All right, so let's go ahead and get started. Thanks everybody for coming, and good afternoon, and welcome to my talk. So my talk is called PI Streams and CI Interfaces. Can a deeper look at the software Cloudy help us find phases in the CGM? So there's a lot of acronyms going on in here. Hopefully all of those will become clear by the end of the talk. So let's go ahead and get started. Basically, we're going to start with an image of a totally manufactured picture of the sky with two very obviously fake galaxies. Because, so galaxies, as I'm sure you're familiar with, are large groups of mini stars, up to like hundreds of millions of stars. They're very bright, but they're very far away, and so they're still relatively difficult to see. We've learned a lot of various physical properties and types about galaxies and scaling relations, like brighter galaxies are spinning faster, have a higher velocity dispersions, or things like that. But a lot of mysteries are still out there. One thing that we have established pretty well is that the galaxy has to live inside what we call a dark matter halo. So basically, the galaxy is not massive enough to have the properties that it's supposed to have if all the mass was just in the stars. We know that it has to be about 100 times that massive. And but that 100 times extra mass has to be in like other forms, because if it was made of normal matter, it would turn into stars, we'd be able to see it. So this extends out much further than the galaxy, so much further that the scale here is actually still wrong, where the real scale is more like this, where the galaxy is about 1/10 as big as the virial radius. And it's full of what we call dark matter, which we call it that because it's effectively invisible to every force except for gravity. So especially it's invisible to electromagnetic radiation, which is how we normally see things out in the sky. We call this distance the virial radius, and that is basically the size at which the internal density of the sphere that is that size is a specifically 200 times the critical density of the universe. So we're actually not going to be talking too much about dark matter in this talk, except for it's going to set the stage for where our material is, because it's dark and we can't see it. So instead, we're going to focus on what's called the circumgalactic medium. So that is the gas, sort of normal baryonic matter that lives inside this dark matter halo. So outside the galaxy, inside the virial radius. And so the main characteristics of this is that it's kind of always in motion. We're thinking about this not just in terms of the gas that's stuck out there, but also that gas is kind of flowing in from the even more mysterious intergalactic medium out here into, at some level, into the galaxy so that it can form stars. And on the other hand, gas is flowing out of the galaxy into the CGM, which kind of can block inflows and is caused by supernovas going off and AGN and other things like that. So to talk about how we study the CGM, it's difficult to study. Basically because unlike a galaxy, it doesn't form stars. So normally galaxies like shine light directly at our face, which is very nice. When we don't have that, then we have to try and figure out what's going on with more subtle methods. So it's possible in some cases to detect quantum emission. So different atoms like emit light at different frequencies depending on their atomic structure. But this depends on density squared, and if you're in a low density region such as a CGM, then this is going to be very hard to detect. So what we're going to look for mostly is absorption spectra, or at least this is how people usually do it. Is what you look at is a background object, so that's this thing, this quasar, and what you say is, okay, if this background object is here, it's shining light through several clouds. And so if I look at the background object and record all of the light rays that it sends out, all the wavelengths of light, it will be missing some when it hits a cloud of gas that can absorb at a specific frequency. So just like atoms can emit at a specific frequency, they can also only absorb certain specific frequencies. And so those frequencies will depend on basically what kind of ion or atom they are. And so at the end of the day, when you look at the final absorption spectra, so in this case, this thing on the right, and it's missing these three things, you can say, oh, it's missing, this cloud is at the characteristic frequency of nitrogen 2, and this one's magnesium 2, and this one's carbon 4, or something like that. So you figure out what is in a cloud by basically what wavelengths are missing and how much you're missing from them. Okay. So we're actually going to be mostly using simulations here. So simulations are very commonly used in galactic astronomy because Simulations are easier to work with than real data in a lot of respects, because we can, one, watch a single simulation evolve with time, which is very nice. So unlike having, just to take statistical properties of galaxies at a certain general era, we can watch a single one. And we can get kind of very detailed data that isn't resolution limited, at least by your telescope, although it has some resolution effects of its own. But the thing about simulations that they require us to, build in a lot of assumptions. So we have to be careful that we don't assume too much about the universe that we don't necessarily know for a fact yet. So we're going to focus on a specific simulation called the Vela zoom-in simulation. And so that is described in this paper among many others. And so the characteristics of the simulation are it has realistic cosmological boundary conditions. So it isn't just like a simulation of sort of artificial boundaries, but we basically ran a dark matter only simulation on a really, really big box to get kind of the cosmological structure. And then we went back and reran certain regions at really zoomed in and good, resolution, which in the galaxy is down to about 17 parsecs. And in the halo, that leads to about 1 kiloparsec. And here's a picture of how the resolution really is in terms of the mass fraction in bins of different sizes. So so we're going outside from 0.1 to 1 RVIR, or actually to 1.5 right here. So the inner halo, 0.1 to 0.3 RVIR, is less than a kiloparsec resolution, 0.3 to 6. If we look at this dashed line, which is the main galaxy I'm going to be studying, Vela 7. So these dashed lines, so we've got less than a kiloparsec, 0.3 to 0.6 RVIR, it's about 1 kiloparsec, and 0.6 to 1, it's between 1 and 2 kiloparsecs, basically. So pretty good resolution in the halo as well. Our simulations do have a few things that are missing. They don't have AGN, which I think it's pretty robust now that those are important to include. So that's a supermassive black hole that's accumulating matter and kind of expelling a ton of energy at the center of the galaxy. And we don't have a couple of physical processes, cosmic rays and magnetic fields, which may end up mattering, but I think we can tell a consistent story even without those. And kind of most annoyingly, our simulation doesn't go all the way to redshift 0. So if our simulation stops at redshift 1, we can think of this as like a time parameter. So this is a simulation that has gone up to about half the age of the universe. And so that makes it somewhat hard to compare to observations, which tend to be a little bit lower redshift. But that's okay. It's basically economical choice to run the simulation to redshift 1, and we get some good data out of it anyways. So to get started, what we're going to do is talk about how we study the CGM. So we said we studied it with absorption lines, but specifically, it can be easiest to study it using absorption lines not just of hydrogen and helium, which are kind of the most common metal, or the most common elements, but using what's called metal lines. And in astronomy, when we say metals, we mean anything except hydrogen and helium, which is sort of not standard in other areas of physics. So you wouldn't think of oxygen or carbon as metals, but we do in this case. And so what you do is, since the CGM is so highly ionized, you'll get different kinds of ions depending on how hot your temperature is. So here's a graph of the different ions that we use to study the CGM at different phases. So the y-axis is the temperature of each one, the x-axis is the density. And so each one of these boxes is the peak density and the peak temperature that you see this ion. So basically, as you go from bottom right to top left, you're going from neutral gas to ionized gas to highly ionized to like extremely high ions. However, I think there is something more to be, we need to be careful using a plot like this, because the actual maximum of each ion isn't necessarily at the spot where this box is. This box is the spot where this is the best density independent of temperature, and this is the best temperature independent of density. But if you have density and temperature effects that both matter, you can get gas that's not necessarily at this point, right? If you're looking over here and you see oxygen 6, you don't want to interpret it as gas that's this low density. So we're going to be a little more careful and say, how does each ion actually come to be? Does it come to be because it's hot, or because it gets hit by radiation, or some combination of both? So basically, the two ways that you make an ion is what's called photoionization, which is where you have an ion or an atom sitting somewhere. Incoming radiation comes in from the cosmological background, or from a local source, but we're always going to use the background in the CGM. And it's going to hit an atom. That atom's going to absorb some energy in its like atom electron system. And then the electron will get released. So this depends on density in the sense that if you have denser gas, you would need more incoming photons to ionize it. So the more dense your gas is, the less ionized it will be overall. On the other hand, if you're looking at the other form is collisional ionization, which is where you have different ions that are running into each other at high speeds. If they run into each other and exchange some energy to one of their electrons, they can knock off that electron. So this depends not on density, but on temperature. So cooler gas is going to be less ionized because they're moving slower, right? Temperature is just really the speed of each particle in the gas. So if a cloud has all of its states created by PI, we say it's in PIE, or photoionization equilibrium. If the cloud has all of its states, I'm going to mute you. Sorry about that. And if a cloud has all of its states created by CI, we say it's in CIE, or collisional ionization equilibrium. So the usual story, the usual way people explain this is to say that hot gas is in CIE and cool gas is in PIE, which isn't totally like unreasonable. There's one kind of complicating factor that we should keep track of, and that is the ideal gas law, which in this really low density region is a pretty good approximation. Hotter gas is going to be less dense and cooler gas is going to be denser. So what do I mean? I mean that if you were looking for like high ions, they can either be in really low density gas, so they've received a lot of photons and that's why they're high ions, or they can be in really hot gas, and so this is why they're high ions. But either way, it's the same gas because hot gas is also low density. So why do we care about CI or PI in this case? And the reason is because if some ions are created by PI and some by CI within the same cloud, then you might have a problem if you interpret them by choosing one, CIE or PIE. Specifically, if oxygen 6 is photoionized and low ions are collisionally ionized within the same cloud, but you use CIE, you can double count that cloud. You can count it once as, okay. And so here's an example of counting these things. So this is in work 2014, where the authors basically went and took the amount of gas, so the solid boxes being the maximum or the minimum amount of gas in that state, the hashed lines being the maximum, and then they basically add together, okay, there's this phase, the cool phase that's in stars and ISM, the cool low ion traced phase, the warm hot oxygen 6 trace phase, and the really hot X-ray traced phase. You add all those together and you get, okay, somewhere between 50% and more than enough baryons are inside the CGM. But if you're double counting these, if you're looking at oxygen 6 and saying this is not the same kind of gas as you get low ions, you might have to cross out some of these. And so you'll get less overall gas as a function of the baryon budget than you think you would if you count all these separately. So what we're going to do is we're going to look at this image here. So this is an output from Cloudy. So Cloudy is a software that basically, among other things that it does, can calculate the fraction of each ion that exists at a certain density and temperature. So what you're looking at here is a contour plot, so kind of like a topographical map, where at the center of these concentric circles is the highest peaks. So you got one peak down here, and you have a second peak up here. And so essentially what we see is that this two peaks are, one of them is temperature independent and cold, so that's here. And the other one is density independent and hot, so that's up here. And should we just like call this photoionized and collisionally ionized gas? And the answer is sort of. That's not an unreasonable thing to do. And a few people have done things like this. So here's some previous attempts to define this. So the first one is in Stern 2018. This is probably not the first one ever, but the first one I'm showing is, so what he did is assign, okay, let's say there are two possible scenarios on which the oxygen 6 gas can live. So the first one is what we're going to call the high pressure scenario, which is this line. So this is like an equation of state for all the gas in the halo. And along this line, oxygen 6 only shows up at this part, so it's collisionally ionized. Or you have what's called the low pressure scenario, which is where oxygen 6 lives along this line. And so it is mostly it's all photoionized. And basically what he did in this paper was try to analyze using other metrics besides oxygen 6, like which of these is actually more plausible line. And we'll come back to this at the very end of the talk. to compare what we see in our simulation to that. Another attempt to define this was in Fireman 2020. So what they did is they drew this nice green vertical line. And they said, okay, on the right side of the vertical line, basically these things are totally density independent. And so these are where collisional ionization is fine. And if you go to the left of this line, then photoionization starts to matter. So it's kind of treated as like a complicating factor, photoionization. So you have to like worry about it. And they notice correctly something that is counterintuitive, which is that turning on photoionization, that is adding, photons coming in to bombard your ions, should create, less low ions and more high ions, but it doesn't necessarily create more oxygen 6, because oxygen 6 will just immediately turn to oxygen 7 just as fast as you make it. So you have to, it's more complicated than you'd think. You don't get more oxygen 6 necessarily when you add photoionization in this area, which is the red line is where they actually find gas in their model. And on the right side, we have one more attempt to define this, which is by Sanchez 2020. So the colors here are a simulation output. I don't know a ton about the simulation, so don't worry about those too much, but basically their definition is inside this hatched region, you have collisionally ionized gas, or oxygen 6, and in this region, you have photoionized. So there's lots of different ways to do this, and we're gonna wanna be really careful, and here's why. This is what our simulation actually looks like. So it's very hard to cleanly separate these, or at least we'll have to be sort of careful to do it, because our gas, so if you look at the green here, which is where most of our gas is, where our gas really intersects with where oxygen 6 is important is right along this border region. So we're gonna wanna be really careful in this area. Okay, so we started with this definition, which, so this is the first paper I'm a co-author on with Santi Roca-Fabrega as the first author. And essentially what he did was we argued that, okay, looking at each temperature, photoionization doesn't end up mattering at all above 10 to the 5.5. Like if you're looking at oxygen 6, it doesn't change its fraction above this value. And in the same way, collisional ionization doesn't really matter if you're below 10 to the 5. So we drew on these two horizontal black lines. And essentially what we did after that was we tried to connect the two so that the CI peak was above the line and the PI peak was below the line. And that, worked okay. And we're actually going to use something very similar here. But what we wanted to do was go back in and get a much more explicit definition, which doesn't rely on thinking about the contour plot by itself, and something that would extend to more ions. So oxygen 7, for example, doesn't actually really have a photoionization peak, yet oxygen 7 can still be photoionized. So how do we define that? And so the rest of this talk, we're going to present stuff from my first paper here, which has been submitted. We recently got a referee report that was favorable, but I haven't responded to yet, but should be published pretty soon. And so we're going to look at oxygen 6 by thinking about how cloudy really works. So the way cloudy actually works is it starts by assigning all the ions in collisional ionization equilibrium. So it basically says, at this temperature, put all the ions in their proper place, and then bombard them with photons, and it'll change their ionization states in various ways. So the point is, if you're dense enough, so here's a density versus fraction plot for different ion states. So if you're on the right side of this, if you're dense enough, then the photons don't really matter. We should think of going from right to left on this graph as basically bombarding with more and more photons. So on the far right side, you're not bombarding with any photons essentially, and so all of these are basically stuck where they are. And as you go from right to left, you start to lose all of your states except the most highly ionized one, oxygen 9. Oh, I guess I never mentioned this. The way we're using these Roman numerals here, oxygen 4, 5, 6, is how many times it's been ionized. So oxygen 1 is neutral, has not been ionized. Oxygen 2 has been lost 1 electron and is at +1. Oxygen 3 has lost 2 electrons, etc. So oxygen has 8 electrons. It can go up to oxygen 9, which has all of them removed. So if you go to low enough density, you become fully ionized. Oxygen 9 becomes 1. Everything else becomes 0. And essentially what we did is we noticed that at a fixed temperature T, so this is a temperature slice, there are only 3 possible shapes to this graph. The first possible shape is if you look from right to left, if you're going and adding photons, your ion fraction increases. So it increases up to some point, and then it'll start to decrease if it's not the most highly ionized, or increase to 1 if it is. And so this is always density dependent, and at high density, it just goes to 0 instead of stabilizing at some non-zero CIE fraction. We're going to call this photoionized, because you're going from right to left, adding photons, you're gaining this atom, or this ion. The second shape is what we're going to call collisionally ionized. So this is where you start out at this high, this flat shelf, and as you add photons, going right to left, add photons per ion at least, you are going to lose your ions. So instead of gaining anything by adding photons, you're actually going to kill your ions and turn them into something else. So photoionization does affect what happens for a collisionally ionized gas, but it doesn't create that ion. It only destroys it if it's following this shape. And the third shape is a kind of a combination of the two. So this is where you have this flat shelf on the right, and then first it increases when you go left, and then it decreases. So this is what we're going to call a transition point, and because, or a transition temperature. So you have some collisional ionization that matters, but then you also have some photoionization that matters. Specifically, we're going to look for where do they matter equally. So where is your collisional ionization fraction exactly half of your total? And that half is reflected by a factor of 2 in this log space, which is 0.3. So when you're 0.3 up from this kind of base value of the shelf, you'll be at equal domination of collisional and photoionized gas. So you can draw a line there to give you a density. So I have here a green line for where oxygen 6 switches over, pink line for where oxygen 7 switches over. And now we have a nice way to define CI and PI gas at any temperature. Because what we're going to do is we're going to take all those points that we just got and add them over here. So those 2 points that we just showed before are these 2 with the stars. So that's at this temperature, 10 to the 5.3, and this is green and pink densities, And so what we're looking at is where is each ion collisionally versus photoionized. And so at each point in phase space, you'll have some ions are mostly made of photoionization, and some ions are mostly made with collisional ionization. So like up here, you'll have everything except for oxygen 8 and 9 is going to be collisionally ionized, and 8 and 9 are going to be photoionized. Whereas down here, you're going to say, oxygen 2, 3, and 4 are collisionally ionized, but 5 through 9 are all photoionized. So this makes this whole idea of PIE and CIE problematic, or at least complicated, because the ions don't all have the same thresholds. Like high ions will be photoionized at much hotter temperatures than low ions will be. So I want to show that this isn't totally crazy by putting this on the actual oxygen 6 contour plot here. So basically we said that our rules were we wanted to split this to be collisionally ionized and this to be photoionized. And even though this isn't like the most obvious way to draw this line, at least it does do that. So it does follow the rules that we wanted it to. What's nice is that in this region that I just said was really important, we have that this is just a temperature cutoff at 10 to the 5.3 basically. Okay. So what does this mean? This means PIE and CIE are going to be kind of hard to use because higher ions are in PIE at much hotter temperatures. If your ion is CI, then your CIE fractions are okay because these are so density independent that it doesn't really have any impact. If your ion is PI, your PIE fractions might be okay, but only if you don't start it off with enough collisional ionized beginning point that it affects where you end up. So if it's highly dominated by PI, then your PIE fractions are probably fine. If you're near the cutoff, which is the case for oxygen 6, then both of these are going to be kind of wrong. So we're going to want to use specifically what's going on in this whole full 2D picture. But yeah. So looking at the simulations, basically the background, so this is a really, really zoomed out image of the Vela simulation, kind of at the limits of what we could really call zoomed in. So this is 6 virial radius in the red circle, and the virial radius is the green circle here. So a galaxy would basically quench fairly quickly if it wasn't able to keep getting gas flowing in. So we see 2 streams, a stream going in from the bottom and a stream coming from the top right. And so one definition I'm going to give right here is that when you're actually looking at sightlines, it's going to be hard to tell where exactly the like clouds are that you run into. For example, if I'm down here, I'm standing here, I'm looking at the galaxy, I'm looking at this quasar, I can see how far apart they are on the sky, but I can't really see where along the line of sight I'm going to run into gas. So all I know is the impact parameter, which is the distance between the center of the galaxy and the closest point on the line. And I don't necessarily know like the actual physical distance from the gas to the center of the galaxy. So we're going to report a lot of things in terms of impact parameters in a little bit. So I just wanted to define that. So we're starting, this paper is a follow-up to a previous paper by Santi Roca-Fabrega that I already mentioned for our definition earlier. But so his findings were, he studied the same simulations as we did and another set of simulations that were an SPH code, so didn't show some of the things we wanted and we haven't been using at the same time. But basically found that oxygen 6 is all collisionally ionized according to his definition, which is basically the same as ours, at high redshift, which goes down with time, and then it comes back up at low redshift if your galaxy is massive enough. So these all go down, but then the low mass galaxies flatten out to 0, the higher mass galaxies start to come back up and become more collisional again. And second, oxygen 6 is more photoionized the further you get from the galaxy. So as this goes out, your collision ionization fraction goes down. So we wanted to follow that up by basically looking, okay, where exactly, what is the structure in the CGM? What does it actually look like? And so what we did was so here is a 2D slice through the center of the simulation. So this is Vela 7 at redshift 1. And what we're looking at is 4 different fields in the same image. So we've got on the top left, the density of gas. So this is just number density of like all gas, and blue being high density, red being low density. So we've got these dense streams. We can see that in the temperature plot, those same streams are cold. So cold versus the bulk, which is low density and hot. And we can see that the hot gas is outflowing at a speed of about 1,000 kilometers per second. Third, we're going to look at metallicity. So this is how many metals there are per unit mass, or how many metals, what's the total metal mass compared to the total mass, the metal fraction basically. And we see these same things highlighted. So these streams are also lower metallicity than the surrounding outflowing bulk, although they are increasing metallicity as you go towards the center. And we're going to interpret that, and we'll talk about this later, as metals being entrained onto these inflowing streams. And lastly, I have this pressure graph. And the main point of the pressure graph is actually to show what it doesn't highlight, which is that we don't really see these objects here. The same thing that was, high density, low temperature, low metallicity. It sort of doesn't quite appear here. There is a little bit of structure here, and the streams are actually at a little bit lower pressure than everything else. But compared to actually the scale of this, it's much more significant that pressure is almost radially symmetric. Right? The pressure at the center is almost equal to the pressure the pressure at the center is the highest, and it goes down as you go towards the edge. So even though this is higher density, it's lower temperature. When you add these two together, you get a pressure that's approximately the same. So what we're going to do is we're going to take our definition that we gave at the beginning and say what happens when we look at oxygen 6. So if we apply that as a binary field to the gas here, on the left we have photoionized gas, and on the right we have collisionally ionized gas. So first comment, I put the arrows back on here since I've just tagged the inflowing streams. So this is the characteristic velocity of these. It's about 1/10 as much as the outflowing velocity in the previous slide. And basically what we're looking at is these cool streams are photoionized and the hot bulk is collisionally ionized. So these are relatively higher density. These are at like 10 to the minus 10 oxygen 6 atoms per centimeter cubed. These are relatively lower density, these kind of redder to orange values. And so basically which one's more important will depend on whether these are more high density than these are bigger. And so we'll go ahead and do some math here. So basically what we're going to do is we're going to add together, how do you get oxygen 6? You have abundance of oxygen. So this is just a constant, doesn't really depend on anything. You have the density of the gas. you have the metallicity of the gas, and you have the fraction that's in oxygen 6. So that's these three graphs here. So if we combine these together, so just looking at the scale of this, this is 4 orders of magnitude from the blue to the red. This is 3 orders of magnitude from the green to the purple. So you can basically combine these and you get that you have about as much oxygen inside the streams as outside them. These will mostly cancel. We're doing this very rough because we'll go back a little bit more carefully later. You have the PI volume is about 10% of the CGM. So I'll show you how we calculate that in a second. And you have the ion fraction goes up to 8 orders of magnitude from this dark blue, which is like about 20% of the gas is oxygen 6, to like, 1 part in 10 million is oxygen 6, 10 to the minus 8. Point here is that if you add together all three of these, the stream should basically dominate. The stream should be a factor of 10 to the 8 more than the, bulk. So we actually are kind of surprised that we don't see more photoionization dominated gas. Because when we actually look at it, and this is the same as Santi found in Roca Faber 19, that oxygen 6 is about 2/3 photoionized in a galaxy of this mass at this time. So, is this really count as dominating? And to look more closely, we have to find, okay, we're missing some collisionally ionized gas by that kind of very rough math. And the thing that we saw when we looked more closely at these images is that if you actually zoom in and you look at the edges of clouds, you have some regions where you have a significant amount of collisionally ionized oxygen 6. So we wanted to know how much of the CI gas was on this interface based on our definition. And when we use that, we get that, okay, about 90% of the collisionally ionized oxygen 6 mass, it lies right on this interface layer, and which only takes up a tiny fraction of the volume. So we think we should think of this as another phase. So the question of PI and CI isn't streams versus bulk. We already said streams would completely dominate that, but it's streams versus these thin interface layers that go on the outer edge. And so if we take all 6 galaxies, so the way that I calculate things on the interface layers is I tag any cell that is itself count as CI, but which is within 2 kiloparsecs of a cell that counts as PI. And when we do that, we get about 90% of all the CI oxygen 6 is inside these interface layers, which end up being about 1/3 of the total oxygen 6 mass in the galaxy. And whereas photoionized gas takes up about 10% of the volume and 90% is collisional. We'll talk a lot more about what these are. But first, let's just take this for granted. Let's say this is real. What will this give us in sightlines? And so the point is, since collisionally ionized gas is substantial only next to these clouds, or these photoionized clouds, sightlines are going to be CI dominated only if the interface is either bigger or it has more O6 than the photoionized clouds. And if you don't hit either a stream or the interface, then you go through the bulk, you basically get nothing. You don't get much oxygen 6. So here's what that looks like. So each of these pixels here is a sightline. So this is just a projection plot, of course, but we should think of it as different sightlines as these impact parameters, where the color of the pixel is blue if you are mostly photoionized, it's red if you are mostly collisionally ionized, and it's white if you are equally both. So we went in and did in the black places where you would get a non-detection, basically where you would get less than 10 to the 13. And that's where you don't hit any of these streams. So the point here is that we have about a 60% covering fraction out to our Vir, and individual sightlines are all photoionized outside of about 0.3 RVir. So inside, they're all collisionally ionized. And the puzzle there is something we'll get back to again when we've talked about the ion fraction inside the interface in the bulk. Here's another look at the same thing. So this is the median oxygen 6 column density as a function of impact parameter. So in the green, we have our total amount of oxygen 6 that we detect. In the blue dashed line, it is the photoionized amount, and in the red dotted line, it's the collisionally ionized amount. And we tell basically the same story, that within about 0.2 RVir, you have mostly collisionally ionized gas. Outside that, you have mostly photoionized gas. And the observations from COS halos are up here, mostly to say, one, we are under-predicting by a little bit, so that is relevant here. But partially it's relevant because our simulations are at higher redshift. We didn't have enough data at this point to make a better, more redshift fair comparison for oxygen 6. But also I wanted to say that if you look at where these are, the impact parameters that we actually measure for cos halos, these are at mostly outside this 0.2 RVR. So these are going to be mostly photoionized if this picture is true at all about these interface layers and the streams. Okay, so this suggests to us this model, basically. So here's some definitions. Oh, sorry. Where we have a galaxy, we have this ambient low density gas over here, which has some characteristic density. We have an interface layer with its own density. We have cool inflowing gas in the stream, and that has a size A. So this is the radius of this cone, basically, and an interface layer with delta. So instead of thinking about CIE and PIE, so to summarize this, we're better served using a combination of both, where some ions are PI and some are CI at a given temperature and density. Oxygen 6 is PI in inflowing streams and CI on their edges, which leads to oxygen 6 sightlines being mostly photoionized if you're far from the galaxy and collision ionized if you're close. But you should have a couple questions. First one is, are these interfaces really like a distinct state, or do they just come from a consequence of my definition of CI and PI, which they totally could at this point, right? If you have streams that sort of continually, smoothly transition from streams to bulk, and that transition went past the oxygen 6 cutoff point before it got to the edge, you'd have what looks like an interface layer that's really just a smooth transition. And second, you know, is the simulation good enough to actually trust it on this? Do observations agree with this at all? So to talk about the first one, are these interfaces just oxygen 6 cutoffs, or are they real physics? Here is two ions that are not oxygen 6. And the point here, so this is carbon 4 and neon 8, which are similar in that they're all lithium-like. They all have 3 electrons remaining. Do the math on that. But you know, they have, this one is a lower ionization energy. This one has a higher ionization energy. And so what this looks like is, let's zoom in on this main big feature here, this big cloud that we've been looking at. These both show the same interface layers. And neon 8 is actually really unique because it shows that you have more neon 8 on the interface itself than you have either inside or outside. So, you know, on the inside, you're maybe too high density, and on the outside, you're maybe too high temperature to get a lot of neon 8. But for whatever reason, these interface layers are highlighted, and we haven't applied any kind of cuts. Same is true for carbon 4. This is a little bit less dramatic maybe, but on the inside of the streams, you have some carbon 4. On the outside, you have none. And on the edge, you can see highlighted in yellow these interface layers. So the point is that it changes fast enough that we think this should count as a separate phase rather than thinking of it as a continuous distribution from the inside to the outside of the stream. And the coincidence is just that oxygen 6 has this cutoff at the same temperature difference as between the streams and the interfaces. So we started looking into what this is, and we asked, okay, is this a shock? Like you have cold gas and you have hot gas kind of slamming into it at high speed? And no, we didn't see these outlined in pressure. Is this a conductive interface? That's relevant, but we don't have magnetic fields, so that's certainly not how we're making this. And what we found was that it looks like this might be a Kelvin-Helmholtz instability layer. So to test whether it seems like to follow those rules, we're going to look at these papers by Mandelker et al. 2020, 2 papers. And here's what Kelvin-Helmholtz instability actually looks like. So this is that paper Joel mentioned by Fielding et al. 2020. So basically what happens, the idea is if KHI will cause cool clouds that are moving past hot low density clouds, if they run past each other at their edge, you'll create kind of a bunch of ripples and stuff, basically turbulence. So if stuff cools faster than it disrupts the stream, then it will entrain more gas into the cool phase instead of damaging the cool phase. And in that, it will also have pressure equilibrium. So this is the assumption of Mandelker 2020, which is that on the interface and on the interface, you have that the density and temperature are both the geometric means of the density and temperature on the inside and the outside. And so you have always rho times T is a constant everywhere. And so if you know the amount of mass that gets entrained and you know the density on the interface, then you can estimate that the radial size of streams should be a power law related to the density, right? Because you know the mass and you know the density, then you know the volume. So if the density of the bulk material is this, then we should see that, and the argument for this is, complicated, and in Mannlicher 2020, you should see that the size of the streams is r to the beta over 2. So whatever power law you have as the density of your bulk material, you should have the negative of that and 1/2 of it as your size of your stream. So the interface thickness is also worth commenting on. So we have reasoned out that it should be about 2 kiloparsecs. It has this smaller fractal structure, which is definitely unresolved. That's what Fielding found. But that its bulk properties should not be super affected. So its bulk temperature and its bulk density. And so its oxygen 6 fraction should be, okay, barring effects of both the magnetic fields that David mentioned and also ionization equilibrium, which is going to be really relevant again here. We haven't talked about it too much, but Cloudy has always assumed ionization equilibrium. And if we're going to assume that, we have to have gas that stays basically in the same place long enough to reach equilibrium, which in our case, if this gas is being entrained quickly, might not be true. So this gives us a little bit more oxygen 6 in the interface. I have an extra slide if we want to look at some effects that have been found for non-equilibrium ionization, but I wasn't going to show it here for time constraints. So are these interfaces Kelvin-Helmholtz instabilities? And the answer is, well, first let's look at its temperature and density. So here we're going to look at blue is streams, green is interfaces, and orange is bulk. So is the dotted line, the geometric mean of the streams and interfaces, or the streams and bulk, equal to the interface density and temperature? Density, yeah, that looks pretty good. Temperature is maybe a little bit more sketchy. In general, in Mannlicher 2020 A and B, these are all assumed to be flat. These are all assumed to be temperature independent of radius, which is not quite true. Our cool streams get a little cooler as we go in. Our hot gas gets a little hotter. So that's relevant, but these are all changing slowly enough that we're going to say these are close to being flat. And then you should see that we have these power laws. If your density of the bulk region is this, r to the minus beta, then your size of your stream A should be beta over 2. If you take this and turn it into a total cumulative volume, which is much easier to measure in the simulation, you'll take this and square it, so you'll get r to the beta, and then integrate it to get r to the beta plus 1. And so your total cumulative volume in the stream should be r to the beta plus 1. And so what we checked was, okay, here's the power law that best fits the density of the outflowing hot gas. And here's the power law that best fits the total volume. And the point is, this should be the negative and plus 1 of that. And so the volumes work out okay. The power laws are pretty much what we expect if we're entraining gas onto the inflowing streams. So we're going to talk a little bit about a model that this suggests for oxygen 6 interpretation and just generally ion interpretation in the CGM by using what might be a bad approximation. So we're going to start with an approximation that these are approximately isothermal, these 3 phases. And the reason that we're doing this is because we understand pretty well what a temperature snapshot looks like for ionization fractions, because we talked about that at the beginning. And since these all have dependencies of about r to the 1/2, less than linear, so we're just going to do that. That may have some effects later. But if you do that, then you can look at these temperature snapshots, which we know what they look like, and check if it's photo or collisionally ionized at that temperature. So in this case, like at this temperature, it would be collisionally ionized because that's the shape of this. We're going to assume that's a flat line and a power law. So power law, I'm going to use the word a lot in the next couple slides. Basically, that just means a straight line in a log-log space. The second kind of thing that you can see is photoionized, in which case you can break it up like this into a power law going down on one side, a power law going up on the other side, and a flat region. And essentially, as long as you don't have, and these are not perfect power laws, of course, don't get me wrong. I know these are more complicated than that, but if you don't go over one of these breaks, if you don't have density change in your phase over one of these, then what you're going to get is going to look like a power law. So what do I mean? Take an example. Looking at the stream has this temperature, 1.6 times 10 to the 4. And basically what we do is here's the densities that the stream encompasses. So it goes from about here to about here. And it doesn't go over a power law break. This is approximately a straight line within this region. On the interface, you have this temperature, 10 to the 5.5. You have densities between 10 to the minus 3 and 10 to the minus 4.5, like here. And so this is approximately flat. It breaks down a little bit at the end, but let's say that it is close to being flat. And if you look at the bulk region, this is the temperature of that. This one has a power law break at about 10 to the minus 5. So above that, it's about flat. Below that, it's falling off. This is all an approximation, of course. If you do that, to summarize, what we expect is that our ion fraction, our overall ion fraction for the streams, is that it's a power law that's declining as you go to higher densities. You expect that the interface is a flat region, and you expect that the bulk has a broken power law that is flat and then it declines. So that's exactly what we see here. This is the ion fraction as a function of radius. So basically what we see is that this green line is flat, this blue line is declining as you go in, and this orange line is a two-part broken power law where one part's flat and the other part is declining. So to get from there to something observable, like total number density, we're going to have to multiply by some other things. So if we take density and metallicity also to be power laws, which for density is pretty good, I already showed this. For metallicity is not quite so good, but let's use it. We combine these together to get, on the left here, the oxygen number density. So this is the total amount of oxygen per centimeter cubed. And these are very, very nice straight lines here. And the point is, we take this, we multiply it by the ion fraction, which in the log space, we just add these. And here is your oxygen 6 number density as a function of radius for each of these three phases. And this isn't just done by presuming these will be power laws. This is just what we find. So the thing that we found is that as long as you don't have a power law break, like you do for the orange graph here, which is pretty undetectable and like not super important like physically, but theoretically, it's nice to see this here. If you have this break, then it'll combine with this other power law and you'll get something confusing. If you don't have one of those power law breaks, you have this flat line or this straight line, then when you add them together, you'll get nice straight lines. So two things to bring your attention to here. First is, since the interface is collisionally ionized, it's flat here, which means that as this increases. So you just get more and more collisionally ionized density as you go closer in. And second thing is something that I want to really make people appreciate about how cloudy works is that usually people would look at this graph, this blue line on this graph, and say below about here, when your oxygen 6 is about 10 to the, is about 1 in 1,000 particles, you can ignore it. Oxygen 6 is no longer important. And I want to make the argument that you can't really, because this is increasing in density so much that even though you're 1 in 1,000 oxygen 6 particles, if you have 1,000 times as much oxygen, you're still going to keep getting oxygen 6 here. And when you add these together, you actually get this almost perfectly flat line. The density doesn't change. You have this huge decrease and this huge increase add together. Now that is definitely going to be a simulation artifact. I don't think that's going to be real. Like just the chances of these exactly canceling is very low. But I think that the idea that they could is really important. It means you do have to keep track of oxygen 6, even when it's outside the region where it's a significant fraction. Yeah, so this is kind of the argument is that any ion will basically follow a power law in here unless it has a power law break in sort of its most important phase, which doesn't happen for oxygen 6 here, but can happen for other ions. Okay, so we're going to move on to the last thing we wanted to ask, which is, should we trust the simulation? And I'm saying it's less about trusting the simulation is right and more letting the simulation help us build an intuition. Because the model that we've presented is a model which we haven't yet tested against observations. This is kind of the next stage, is to use this model. But it has 3 different phases to the CGM, with 2 of the temperatures independent, with tunable parameters for the size of the streams, the size of the interface, and sort of the number of streams. And where inside it, each phase is a power law for each ion, more or less, unless you have one of these circumstances where one of the ions has a power law break. So we're going to compare this to a couple of observational papers, or at least kind of phenomenological observational papers. So first we're going to look at Stern 2016. So basically he proposed a model to fit the cost halos data because he saw that high ions can come with, or low ions always come with high ions, but not the other way around. Sometimes you'll run into a high ion that doesn't have any accompanying low ions, but you never run into a low ion without accompanying oxygen 6, basically. And the kinematics of the two agree when they both are present. And so he
By
argued.
the way, okay, you don't see lower, you do see, so what?
So what you get is that the low ion clouds are basically inside of the high ion clouds is the idea. So you have these tinier, denser, more low ionized clouds inside these larger, less low ionized oxygen 6 clouds. And so to get into the tiny clouds, you have to go through the big cloud first. So you'll always get oxygen 6 and you'll get the other one, or you can go get oxygen 6 and not get the other one. But you can't get to the tiny cloud without going through the big one first.
Thank you.
So the consequences of this are that if you're below some certain, so this is oxygen 6 column density versus H1 column density. And the point is, below some critical H1 column density, you sort of have not gone through the cloud you need to get oxygen 6. And above that density, you have gone through that cloud, but you don't get any more. You go through these, if you go through something with 100 times as much or 10,000 times as much H1, you're not really getting any more oxygen 6. And the idea is these high density clouds are just not producing oxygen 6. They're really just producing lower and lower ions. This is where you're running into the other states. And this was part of a panel. There was a bunch of images like this for basically various ions. Each one had kind of their own characteristic cutoff point, at which point it would flatten out. So we wanted to compare to that idea and just say, okay, we actually get something very similar. And we fill in this region where they only got non-detections, which is kind of nice. So by running a bunch of simulation or a bunch of sightlines through the simulation, we fill out this structure pretty nicely. And so we can argue, okay, maybe these inflowing streams are the structures that can give us Stern 2016 results, but we have to interpret it a little bit differently. So if you don't go through any streams, you're going to end up over here. You're going through just the bulk area. You saw nothing basically. If you go over here, then what's happening is as you go closer and closer in, your oxygen 6 fraction is going down so much that it's canceling out basically the increase in density. So you're getting much more oxygen at a much lower rate converted to oxygen 6, gives you basically a constant amount as you go to the right. But as you go here, you'll start to get more and more low ion states. Whereas, over here, you're going to get less of those low ion states. So a second paper that we are comparing to, and this is kind of a more kind of heuristic comparison, which I have a little bit of data for, but I have cut for sake of time, is comparison to Stern 2018. So basically in Stern 2018, which is the paper I mentioned way at the beginning, an attempt was made to disambiguate a photoionized and a collisionally ionized scenario for oxygen 6. So we noticed that oxygen 6 is mostly seen from outside about half the virial radius. So even though most of the sight lines were within half the virial radius by impact parameter, remember that impact parameter is just the minimum distance and not the overall distance of a certain cloud of gas. And so if you actually do a transformation on it, called an inverse Abel transformation, then you'll see that it seems like most of the oxygen 6 is actually from outside that region, and that oxygen 6 is mostly photoionized. So, and I have a slide for this next slide. But at the time when he wrote this, no simulations could actually see that oxygen 6 was mostly photoionized, or at least he made the point that most simulations that he saw didn't really do it, and the ones that did sort of were unphysical in other ways. So you look at that, the comparison. So here is the density at which he found oxygen 6 could really live according to a bunch of different constraints. So, each of these lines is a different constraint. This green line is like using NO6 versus the width of 06. This is the C1 line, et cetera. So if your oxygen 6 comes from photoionized, then all of these pieces of data agree that it has to come from this position. Actually, so the point is this excludes collision ionization from being right, at least if all of these other things are in the same place as it. So it's not in collision ionization equilibrium. What?
Where is the collisional ionization? To the right?
Well, collisional ionization would be further to the left, basically. It'd be lower density because it'd be hotter.
Okay.
And so we want to, just to put a long story short, a global structure that would give us most of the oxygen 6 is in the outer halo and mostly photoionized, which it needs to agree with this, we can provide an idea for that structure as the cool streams that we're talking about. So our simulation is one of the only ones that's finding oxygen 6 mostly photoionized. So if you want to try and tell this story about photoionized oxygen 6, you might need to kind of invoke these inflowing streams from the IgM. So that is kind of the summary of that paper. And now what I want to do next is move on to some future work. First thing I want to do is a better and more detailed comparison of observations, right? The two things we just listed were pretty heuristic, both for reasons of redshift, because we didn't have enough data at redshift 1 and to compare with our simulation, which when we get there, and also for reasons of the model, which what I want to do is compare three things. I want to compare the simulations versus the observations versus the model. And the thing that was really key there that we didn't have is the observations, which are now coming online. So the especially exciting one is what's called the COSBA survey, where we've gotten neon 8 data from Burchett 19, we've gotten oxygen 6 data from Prochaska 19, and we'll get sort of more connecting data in the near future, which gives a lot more observers, some of which are even out at redshift 1. So we want to compare the oxygen 6 data there with the model and the other ions, especially high ions, and see if we get values which agree pretty well or better than other kinds of models. And if not, why not? And this includes going a little deeper into the actual spectra. So I haven't showed too many spectra over the course of this, but we have looked at them a little bit. And basically, the way a spectrum works is it doesn't just have one kind of nice V shape, but it has usually several, where each one corresponds to like a different cloud moving at a different characteristic speed. So if you look at, for example, this cell here, you have neon 5 and silicon 3. Neon 5 has 2 peaks, silicon 3 has 3 peaks, but 2 of them agree and 1 of them doesn't, right? So what's different between the cloud of gas where we had silicon 3 but not neon 5 and the cloud of gas where we have both? So which ion should align, basically? So one thing we can do in a simulation is we can actually just look at this. So this is kind of cool. Here is a spectrum of, say oxygen 6 versus carbon 4. So they've been shifted, so they're in velocity space, so they are overlapping each other. And basically you see, okay, here's 3 components of oxygen 6 and 4 components of carbon 4, where they mostly align, except in one of them we have more carbon 4 than oxygen 6. The other one's oxygen 6 is more important. And looking at that in the simulation, we see that's because we go through this structure where the carbon 4 is kind of a small, thinner filament that lives inside the oxygen 6 cloud. So these are overlapping clouds, but carbon 4 is only mostly important at this one versus this other one. So this is in the plane of the sight line. So we want to do a little bit more analysis like this and see if we can get some good, images to demonstrate in what cases we have overlaps between different ions and what cases we don't. And we want to focus on oxygen 6, carbon 4, and neon 8, mostly because they have that high redshift data that we can compare to. Second thing we want to do is some work that's already been started in the Agora collaboration. So this is basically a combination of a bunch of different simulations who basically took the same initial conditions and said, okay, we want to use the same initial conditions for and run our own different codes on those and see what we get out, basically. Each of these is like a professional code. They all make nice results that look like galaxies, but they look different. And so how do the codes create different galaxies out of the same initial conditions could tell us a lot about what matters in each code. And what we really want to look at is the CGM, which we haven't done yet. We've done other papers comparing kind of star formation histories and stuff. But one thing that I'm excited about is to look at what happens when you use SPH codes and see if you can make these interface layers. So an SPH code has uses particles to determine where gas is rather than a grid. And without a grid, is it hard to create kind of stable interfaces that protect cool gas? And if it is, then maybe that'll help, differentiate whether this is a good method or not, depending on which, actually gives you better, more observational aligned results. The third thing that I'm looking at is to talk about how do different feedback prescriptions change the CGM. So basically, here's the Vela Gen 6 that we've been studying at the top. These are the same images we showed already.
You mean Gen 3?
Oh, yes, sorry, Gen 3 at the top. Gen 6 is at the bottom. So this is basically when we rerun the simulations again, but with higher feedback. And what effect that has is, we haven't totally studied these enough, but just very preliminarily, what we see by turning up the feedback is that these are much more fragmentary and smaller, and their interfaces seem to be much more important, and it actually fills some of the space that's not directly aligned with these inflowing streams. So collisionally ionized gas, which is on the right, seems to be getting more important as we turn up the feedback. And last, I want to look a little bit more into the whole ionization structure of the CGM. So this is actually work by some some science internship program students that I had over last summer. But basically what we looked at was the distribution of oxygen into all of the possible states, and not just the visible ones. So the visible ones being oxygen 6 for the most part. But if you look at this, you have oxygen 6 is actually a local minimum. You always have less oxygen 6 than you do oxygen 7 or oxygen 5. And even more strikingly, if we apply our definitions of PI and CI from the beginning of the talk, most of these ions end up being photoionized. Oxygen 2 through 6, and even oxygen 8 end up being mostly photoionized according to that definition. Whereas collisional ionization really only is dominant on 2 states, oxygen 7 and oxygen 9. Oxygen 9, of course, is completely invisible. It has no electrons, can't really interact. So oxygen 7 ends up being kind of, if this thing is true, which we haven't done enough work on this to really prove that this is general, or if this just depends on cloudy, or even if it just depends on Vela. But we found that this is very robust in Vela. This is true at almost every redshift we've looked at and every simulation mass. And oxygen 7 is the only one that's collisionally ionized. And this same shape is actually true for carbon and neon. So with lithium-like, helium-like, hydrogen-like. So, neon 8, 9, 10, 11 have the same structure here. And so we think this is really interesting. And we think this is why Sandy asked at the beginning, is oxygen 6 really nice? I really wish we could see oxygen 7 here, because if we could see oxygen 7 pretty well, and I know that some people have started to do observations with it in the Milky Way, but if we could do that, it's actually mostly collisionally ionized. If this ends up being general enough, if we can check other simulations and sort of figure out why this phenomenon happens, collisional ionization is much easier to interpret because it's flat. We don't have to deal with that extra complication of ionization fraction changing. So if we could get collisionally ionized oxygen 7, we could actually get a much better kind of constraint on the gas that it's in and the temperature and density of it, stuff like that. So that is all I have. So thanks everybody for watching. And yeah, I welcome questions, and that went a little longer than I thought it would, so apologies about that, but I'm gonna leave up a conclusion slide and then we can, let's just talk about it.
So usually at this point, we would have a long discussion with the audience, long or short anyway. But because X has to leave very soon, why don't we give X the first shot at asking any questions, and then maybe you can tell me, at least privately, whether you think that Clayton passed.
Will do, and I think I hit him with my key questions, so I'll defer to the audience and listen in.
Okay then, thanks Clayton. Any questions from the audience? Including, of course, members of the committee. Sandy has her hand raised, and I think David Koo.
Joe just did too, yeah.
And Joe also.
I see huge value in what you're doing, Clayton, because you've got a situation in which you're applying some known physics and you look at the consequences and you're coming up with rules and interpretation. That's wonderful. What I don't understand so much is whether or not you're actually studying real halos. And I'd like you to comment on the major deficiencies in these models that might mean that, in fact, real gas is distributed differently. Not that your rules are wrong. Your rules may be quite right, but the pictures that you're studying might not fit the real halos.
Yeah, I mean, there's definitely a number of things that are going to be off about these. So part of it is going to be the physics of them. I actually made a nice slide with all of the physics that we didn't include?
Didn't include, that's probably what I'm asking you about.
So, should we trust the simulation? And like the real answer, I think, would be just no. I think we don't want to necessarily trust the simulation to be like accurate. But what I think because we don't include magnetic fields, which as David mentioned, but also as this recent paper, Nelson 2020 found, lets us get low ion states in kind of small clouds that otherwise would get destroyed by hot outflowing gas. And especially because we don't have AGN. I think that's like the biggest thing that we're missing here in these simulations in particular. So AGN are pretty well shown to be like super important for making the CGM have kind of the right temperatures and heating up to the level we expect, and like having very, quenching happen at reasonable star formation or stellar masses and stuff like that. So the fact that we don't have either of these things should mean that, yeah, we should be very skeptical of this. But
can you already see sort of like massive contradictions between the predictions of this particular halo and observations?
I mean, not necessarily. It's honestly, it's hard to tell because a lot of the like most direct observational comparisons would be to things that are not exactly that are not at the same redshifts, and so have changed sort of significantly since this point. So it's hard for me to just say, okay, this simulation is bad enough that it's wrong and we shouldn't use it. I think I'd prefer to be like, okay, the simulation is suggesting a way to get these kinds of structures that Jonathan Stern proposed would be able to regulate the CGM in the way that we expect. I think actually another one thing I want to mention that I don't have a slide for, but is especially low ion states. I think we don't have the machinery to make those in the simulation. Resolution is not quite good enough. If you say Cameron Hummels is right that we need higher resolution to get low ions. And also, I think that low ion states in outflows have been seen, and our simulation just can't make those at all, right? Outflows are basically always going to be hot and high ions. And so if we see low ion states in outflows, they have to be protected by something really powerful on, protecting these clouds from getting destroyed. And some recent work has shown that this can be done. Some simulations have started to make these and sort of really idealized simulations, but we don't have that yet. Does that answer your question? I'm not totally.
That was pretty good.
Okay.
Are you done, Sandy? I'm sorry, I don't want to interrupt.
I am, yes.
Move you back onto my main screen.
Yes, I have a question about kinematics, and that is, you expect that if we, as an observer, when we observe through, let's say, these interface layers, and I can imagine that if you look at the outer regions of the galaxy, let's say RVR and stuff, you would go through those interface regions for the collisional part. But the inside, of course, it's due to a lot higher density and other things happening there. So can we use kinematics in some way, maybe the B parameters as an independent temperature gauge, and then look at the shapes of those if we had not high resolution spectroscopy to then say that, yes, in fact, your model makes a lot of sense. We are going through these little layers, they have little funny spreads, and then you go through, the photoionized part, and then you go through the collisional part again, and etc. Can you take advantage of the kinematic structure at the interfaces as a way to check out your model?
I think, yeah, I think that the interfaces should be very turbulent. So they should basically look more, like the whole famous problem is like when you're looking at kinematics of an ion, you're looking at, okay, it's both got some temperature width and some like non-temperature broadening. And it's hard to tell the difference between those. But if you say, okay, this is collisionally ionized gas, then its temperature is actually fairly well constrained. If you say this, and of course you know it's true, which we don't always have, then you can say, oh, the rest of it comes from thermal broadening. It makes sense that this has a wider temperature broadening than we thought because it's actually mostly thermal, or it's mostly turbulence on these interface layers.
I'm really suggesting that maybe you want to explore that aspect of checking out your model.
No, that's a good idea. I think I would. Yeah.
Is also related. That is, right now you use the term clouds. I've heard that several times. Then you talk about streams. But in fact, if you have things, I think people talk about drizzle, like fog, etc., where there's actually lots of little regions. And so this actual physical or the 3D structures of these things could also be an important part of deciphering whether your particular model versus that of other people with maybe different ingredients, etc., is really closer to the reality. So I was wondering whether you can think along those lines as well, because I can imagine that if the same volume, but you have them in terms of lots of little smaller structures, you have, of course, a greater surface area, for example, right? And so there's a balance between surface area, volume, temperature, density, et cetera, that might also be another diagnostic. So just, again, another suggestion, and do you think that's really helpful, perhaps?
Yeah, I think that is helpful. I think that's a good way to kind of interpret this. And if you can run into like a big oxygen 6 component with less turbulence and a smaller one with more turbulence, maybe you can try and interpret that as these two things.
And the third part, of course, is the frequency. As we get more observations from the Burchetts and the X's of the world, you'll get statistics of the relative fraction for a given impact parameter. And that, again, would be telling you the rarity and, again, maybe the 3D structure and the volume surface relationship again. So I think maybe as more data comes through, well, the people like X and Joe should answer whether they can get enough data to even deal with these statistics. Maybe it takes too much. I don't know.
Well, if I could chime in on
absolutely, I'm shutting myself off.
No. So some good points there, but I just wanted to chime in on the issue of kinematics and what we can do. Some complications from the observational realm. You mentioned high resolution spectroscopy, and for redshifts less than 1.5 or even 2.5 for oxygen 6 basically doesn't exist and won't for many years. So it costs, essentially the resolution is poor enough where it's been shown that I don't think it's actually I don't think the observational evidence has been published yet, but basically we can't resolve the very cool photo ionized cool gas structures that we might like to see, that we might like to have as that independent check in terms of the kinematic evidence for these cooler structures reproducing the photoionized contribution. So that's a complication just from observations. It's particularly for Hubble. Essentially, there's just to observe with STIS, the higher resolution modes, we would have to have just super bright quasars that basically, I think there's like one, and that's the study that I'm talking about. We observed it a couple of years ago, and are in the process, and sure enough, we see something that looks like a well-behaved, relatively broad oxygen 6. Looking at the higher resolution, and it breaks up into these little cloudlets. So it's really tough at these redshifts for these ions.
For now, but the future may have UVAR or whatever. You got a gigantic UV telescope.
Oh yeah, preaching to the choir. Let's do it.
Right, as a theorist, he can predict what we might be expected to see in the future. Now, it'd still be interesting. At least it's tied to reality. Definitely.
And anything that helps make the case for a LUVOIR, for example, is certainly applauded in my book. But if I could just get to a couple questions I had for you, Clayton. One of which being, so thinking about comparisons to COS halos and lower redshift, there's obviously a redshift mismatch between the simulation that you're analyzing here and COS halos, which is about redshift 0.2. And so you showed the nice figure from Roca Fabrega et al., where the collisional ionization contribution increases at lower redshift. Thank you. And so in terms of like connecting the physical picture from what you're seeing in the simulations to what we might be seeing in COS halos, for example, do you worry that this introduces a complication as to, well, maybe it's simply, and the halo masses that you're interested in, both, I mean, definitely for COS halos are right around this 10 to the 12, 10 to the 12.6, where indeed we do have the collisional ionization fraction increasing at lower redshift. You worry that that's sort of that effect alone ambiguates the physical connection, whether we could actually have these the dominance of the photoionization in the O6.
Can you restate the question part? I think I got lost a little bit.
I
Sorry.
didn't understand the question either, Joe. So try again.
Sorry, it was too long-winded. Your results for all of the for the large photoionization contribution of oxygen 6 in your simulation that is at higher redshift. Do you worry because of this evolution in how much is produced by collisional ionization versus photoionization, particularly at late times when cos halos is really constraining? This would be here about a redshift 0.2, that the two aren't necessarily comparable.
Yeah, like that it switches back. Like in this picture, it becomes more collisionally ionized again.
That's right.
I think that's totally possible. And yeah, I think one thing that I would say about this picture is kind of the reason that I want to that we wanted to go through this again is because this picture is integrating the entire CGM as a one big bubble, and it's not really thinking about the difference between gas on the inner part of the halo and the outer part of the halo. And why that matters is because the inner part's way denser, but the outer part gets overrepresented in the sight line because the sight line goes through the outer part, and it spends more time further out in some respect because it's goes through the CGM to some minimum point, but it spends most of its time outside that minimum. So when you look at sightlines, this actually doesn't change a ton with redshift. So I'll just show a picture. As you said, this doesn't go to redshift below 1, but this does show how it evolves at redshifts above 1. And it doesn't really change that much. The general story is still that collisional ionization is dominant on the inner part of the halo, and photoionization is dominant on the outer part, except the transition seems to be happening further out at redshift 3, and then it moves into about 0.5 RVR at redshift 2 to about 0.3 RVR at redshift 1, as you saw. So it seems like we're getting more photoionized, which is exactly what we saw here, right? This is going from mostly collisional to mostly photoionized. And in principle, yeah, the next stage, the next phase, the next line, which would be, let's say this red line, which these came from the Nihao simulations, because so they go to redshift 0, which is why we can see what they do at redshift 0, is they go back up. So we might expect that this, goes back to collisional. But I think that this structure, that the inner part of the halo versus the outer part, will still be mostly photoionized on the outer impact parameters. But all of this said, I think this is very simulation dependent. And if the simulation, for a variety of reasons, has various problems, we might want to kind of reevaluate which of the two will be more important, and specifically the densities and temperatures of the streams. If those are changed a little bit, you might change kind of the relative importance of these things, even if you keep the same overall structure. That makes sense. So using these as tunable parameters may be still better than trying to fit them to the parameters from Vila, because I don't think those are necessarily going to be accurate.
Thanks. More questions from people?
Sandy has her hand up again. Go, Sandy.
A related question. I hadn't thought about this before, but this evolution with Z. I'm thinking now of the Eagle simulations, which are low resolution simulations and probably don't tell us anything about the actual structure of halos. But the interesting thing about what they predict is they predict that during quenching, actually halos empty out and then refill later. And I just wonder where that kind of picture fits into either the simulation or actual data. Do we see any evidence that halos are actually doing that either for real or in a simulation?
Uh, I don't think that whatever feedback we have, if we don't have AGN, it's not going to be strong enough to do
It's,
that.
I'm sure you're not seeing it in Velo.
Yeah.
No.
So we aren't running into that.
Uh-huh.
In terms of whether it works with this picture, I think that if it clears out the halo, I think might be easier to think of it in terms of what happens to these streams, because we want to say these streams are the fuel for star formation. So if these things can get disrupted, which in the language of near Mandelker 2020 A and B, which is where we got a lot of our Kelvin-Helmholtz instability stuff, if the disruption time of gas in the KHI is shorter than the cooling time, then they'll disrupt the things instead of cooling and entraining onto them. And so if you turn up the feedback enough, or you reach some critical amount of stars that have formed enough supernovas that create this feedback which is strong enough to quench you, you'll probably disrupt these streams instead of letting them through. And if they can't get through, maybe they start to, like, they lose a lot of that momentum or something. I'm not really sure how they would turn around and empty out the halo, but maybe you just expel a lot of stuff. Once these streams are gone, they can no longer block your outflows, and those outflows will just go all the way outside the halo.
I'll just mention in connection with this AGN stuff that we have access to 2 sets of simulations that have AGN and are reasonably high resolution. One is TNG50, and all of TNG50 becomes public as of February 1st, and the 2 co-PIs, Annalisa Gillespie and Dylan Nelson, are collaborating with us. So we'll have complete access to TNG50, which of course has AGN. It's not as good resolution as, it's more like about 100 parsecs, not the 17 or 25 or something parsecs that we have in the galaxy. But in the CGM, it's pretty similar. The other one is the New Horizons simulations, and those also include AGN, and they're run with a code very similar to the code that we use for Vela. It's the Ramses code, which is in many ways very similar to ARC. And so we have access to those, and we're also going to be running those. So, so there will be plenty of time to look at the results in fairly high resolution simulations that do include AGN. And we'll see if that tells us that we're pushing out the baryons in the halo as in the simpler Eagle type simulations.
Another comment, and that is, I realize that there aren't that many high resolution simulations that work with clusters. I believe New Horizons may have one cluster that they're considering, or some large group.
No, actually not.
Oh, they're not doing it anymore? Originally, they said something about possibly doing that.
Anyhow,
well, the point I'm going to make, that's regardless, the point that I'm going to make is that the cluster is a different type of environment that might be a way to check out some of the physical properties of the clouds and streams and the amount of oxygen 6. And I don't know what you might expect in, let's say, the outskirts of a rich group versus a very, very large cluster, but we are finding plenty of those things at high redshift. So lots of opportunities for quasars in the background to study a few of them. Joe might be able to better address, because I know he studies these type of things. Are there clusters and groups that are actually being studied with regard to oxygen 6, or maybe, and see if that's possibly a useful probe for Clayton's picture of the interface layers?
Yeah, so we've studied just that oxygen 6 in cluster environments at low redshift, and I can tell you that at low redshift there's basically no oxygen 6. There's very little H1, as a matter of fact, and I would say that moving to higher redshift is a frontier. Yeah, it becomes difficult because looking for background quasars at redshifts that are clusters that are known at redshift 1.5, 2, where we could start to get some of these diagnostics from the ground are pretty few. But I've been trying to look at some with integral field spectroscopy to try to directly map the cool gas in emission. So perhaps that could give some path forward.
Anyway, just
So,
a thought.
the
Again, since you're doing
simulations-
theory, you can predict all kinds of things that observers have yet to gather data for.
So the
Absolutely.
simulations that we'll have access to that will have at least very dense groups of small clusters, about a 10 to the 14 or so cluster is in TNG 50. I'm not sure how much Clayton's analyzing such a thing is very complicated.
Yeah, a cluster would be real different than this because at least this has like a nice, a center, and then you go outwards from the center to, the edge of the galaxy, whereas clusters have so many different like important mass things that could affect it. But, still worth looking at.
So any last questions?